right, we're going to continue talking about light. Our lesson objectives will describe blackbody radiation, we'll describe the photoelectric effect, and we'll distinguish between line and continuous emission spectra. And finally, we'll describe the particle nature of light. So we've already established that light can act like a wave. This is well known at the time that we started making discoveries in this realm, and it was widely accepted to be the explanation for light over light acting like a particle until the turn of the 20th century. There were several experiments that did not fit into the mathematics of light as a wave in calculations using electromagnetic relationships. The first was an in-depth study of blackbody radiation. So what is blackbody radiation? When you heat a material up to a sufficiently high temperature, it will give off light. Examples of blackbody radiators include the sun, though it's important that it's an imperfect blackbody radiator, incandescent light bulbs, and that's in the middle there, a nice little picture of an incandescent bulb. You may have never actually handled one, but let me tell you, it was not fun to change those out when the bulb failed, which it did frequently because they were super hot. And finally, iron being smelted. On the right hand side we have a picture of that. The liquid metal is glowing. In fact, every picture of an iron forge that you will ever see will have a glowing liquid metal. The fact that these materials glow when sufficiently hot can be partially explained with classical modeling. But the light emitted by a blackbody radiator depends on the temperature of the material. We'll look at this on the next slide. All right, so if you plot spectral radiance, or how bright the light is, versus wavelength for blackbody radiators at different temperatures, the curve can be modeled using various theories. The black line that goes up to infinity is what happens when you apply light as a wave to blackbody radiation. It doesn't work. It doesn't fit at all. So these spectra cannot be modeled for visible or UV light using classical methods. Max Planck discovered that if you use quantized energy, you can predict the shape of this curve. He said E equals N times H times V, or nu rather. N is an integer. H is a constant, which we now call Planck's constant, and nu is frequency, like it was before. While we have this graph up, notice that at the higher energy, or the higher temperatures, the wavelength that predominates gets smaller. This goes along with the wavelength and energy being inversely proportional that we learned about last time. So the fact that it doesn't go with classical theory, bit of a pain, but the fact that we have an energy and frequency relationship that makes sense, great, that squares. So what about the photoelectric effect? The photoelectric effect happens when you shine light on metal. If the light has a frequency over a certain value called the threshold frequency or work function, which is incidentally dependent on the type of material, then the electrons are emitted with a kinetic energy proportional to the frequency of the incoming light, not the brightness of the incident light. So why does this conflict with our understanding of light at the time? If light is a wave, then it is transferring energy to the metal. So why would that cause electrons to pop off? Electrons are particles. Wouldn't the metal just heat up? Why does there need to be a certain frequency of light before the electrons are excited to come off? And finally, we know that brighter light equals more energy in classical terms, so why would that result in electrons that don't have higher kinetic energy? So how can you explain this? Einstein earned a Nobel Prize for explaining it. He looked at Planck's conclusion that energy was quantized and applied it to the photoelectric effect. He said that waves were particles, which we now call photons. And the energies of those particles were given by E equals h nu and E equals hc over lambda. So yes, we've already used this equation, but it comes from Planck's explanation of blackbody radiation. From there, Einstein said that the energy needed to remove an electron was the work function, given by a circle with a vertical line bisecting it, otherwise known as uppercase Greek phi. And the amount of energy the electron had was equal to the energy of the incoming light, h nu, minus phi, which is the work function of the material. And it worked. It explained what was going on, and it was simple. And the best scientific advances are often really simple ideas that make everything elegant and make it possible. Einstein essentially said that waves were both wave and particle. And then it depends on the application. So this was crazy pants idea as far as they were concerned at the time, but it explained what was going on, so maybe it's true. Which brings us to continuous spectra and line spectra. A continuous spectrum is given off by a blackbody radiator like the sun, and it's seen as a rainbow on the top line. So that first line is a continuous spectrum. Continuous spectra represent a wide range, or all the wavelengths of light. These spectra are seen when lights are made by heating a material. So also the sun. Line spectra were also being observed. These spectra were made by atoms or molecules. A sufficiently heated material can emit a line spectra instead of a continuous spectra. It is easiest to make these with a gas that has an electric current pass through it in an instrument called an arc lamp. Each element gives a distinct line spectra. As you can see here, we have sodium, we have hydrogen, we have calcium, we have mercury, and none of them look the same. Line spectra have discrete wavelengths that are characteristic of the element that they are emitted from. Elements with more electrons tend to emit more lines in the line spectra. It's not a perfect correlation for what you see here, but if you include the other parts of the electromagnetic spectrum, not just the visible, you would see that there are more lines the more electrons a material has. Right, so we go from not a lot of lines to much more lines as we get more electrons. That gave us a mental correlation. All right, to summarize, blackbody radiates a continuous spectrum of light when it's heated to a sufficiently high temperature, and this works for metals. Photoelectric effect says that electrons are emitted from a metal if you shine a light beam with sufficiently high frequency at it. The electrons have an energy that is equal to energy of light minus the work function, and the work function is the minimum amount of energy needed to eject an electron. Finally, line spectra can identify elements by the unique discrete lines in the spectrum.